Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He's not only focusing on theory part, he's doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exams to test our knowledge, and as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently, I was searching for digital marketing courses online in Google, and I came across XLR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped, so I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, XLR.
I came to know about this course from my college. Actually, for learning platform, this is very nice, and I learned from here ChatGPT and AI from online. Vikas is teaching for me for AI generative and ChatGPT. We are using this technology in more. And after finishing the courses, I came for collecting the certificate. I seen the classrooms and faculties. Classroom is very nice. After the completion of exam, they will give gift and certificates. Thank you, XLR, for giving these courses. I learned a lot from this. I gained the more knowledge from here. And thank you for XLR for teaching us.
Hello guys, I'm Vikram Mahajan and I'm studying in Swami Vivekananda Institute of Technology College, and I came across a training program which was mobile app development using Flutter, which was given to us by XLR Solutions. I came across this program through my college faculty, who told us about this program, that it is a very good course and you should enroll in this course. So I enrolled in this course, and initially I felt really good about this course because they started everything from a very basic point of view, that even if someone who doesn't know anything about Flutter or anything about mobile app development can also learn the same way the ones who know about it are learning. So no student was left behind and everyone was given equal attention. All the doubts throughout the course were cleared. And if we had any questions also, we were like, the trainer was also ready to stay for a longer time than it was scheduled, even for the sake of doubts. So that shows how important the students are to them. So it was a really good experience with XLR's program, and by the end of the training program, I was able to develop my own application. And through the development also, there was another point. So our sir taught us about how we can connect our own mobile phone to our laptop and write code in our laptop, and you can see the output in your phone, which is really creative and interesting for me. I felt really good about that. So in the end, I developed my own mobile application. I showed it to my mother, I showed it to my friends. I felt really good about it. So I would really suggest XLR.
Dear faculty members, I hope you all doing well. Okay, good afternoon, sir. Amritsar, is I'm audible?
Yeah, yes, Shmita.
Yeah, you can start the sessions.
Okay. Good evening, all. I'll share the screen. Okay. Okay, so today we are going to speak and discuss quantum computing advantage. So till yesterday, we were discussing about the basics of quantum computing. So today we are going to increase the level a little bit and explore the software implementation of quantum computing principles. So before that, before starting today's session, let's have a quick recap. So what did we discuss in the last 2 days? So we discussed about single qubit systems. So where every quantum system or every quantum computing applications can be broken down into fundamental units of qubits, similar to classical bits in the classical electrical, classical computational systems. And these qubits can be implemented in the form of electron spin because electron spin has two definite energy levels, which can act as 0 and 1. And these qubits can be represented in various forms for mathematical operations and calculations, such as vector space representation, where we represent the qubits as vectors in a vector space spanned by various standard basis vectors, such as ket 0, ket 1. There can be other basis states as well, like ket plus and ket minus, or ket I and ket minus I. Then we spoke about multi-qubit systems, where there is not just one single qubit, but more than one qubit. And to represent them, we learned about tensor product formalism, tensor product tool. And thus we were able to represent states like ket 000 plus ket 1011, etc. And all of them have a matrix representations as well, such as ket 0 can be represented as a 1 0 column vector, and ket 1 is represented as 0 1 column vector. And we understood how states are entangled, and because of just a second. Okay, hi everyone, I'm back again. These were the things we were discussing in the last days. Then we discussed about quantum gate operations, where there are certain gates that are specific to quantum computation. Like we have a Hadamard gate represented by H, and we have gates such as X gate, Y gate, Z gate, and these are called as Pauli gates. X can be represented in a matrix form such as 0, 1, 1, and 0. And what it does is it simply flips the qubit. If the qubit is in a 0 state, it flips it to 1, and if it's in a 1, it flips to 0. Similarly, we have the Y, which is same as X, but with a negative sign. So I have 0, 1, and a -1 here, and the 0. And then we have Z, which is represented as same as an identity matrix, but with a -1 in the second column, 1, 0, 0, -1. And we also came across another gate, which is called as C naught. This gate is also quite important, and it is one of the gates along with the single qubit gates forming a universal set of gate, which means we can represent any quantum circuits using only these gates. That is a single qubit gate such as Hadamard and the Pauli gates, and 2-qubit gate of C naught. And we haven't discussed the matrix representation of C naught yesterday, so I'll take a minute or two to look into that. So what does C naught do? C naught, when applied, okay, I can also express C naught in this way, CZ, another shorthand for C naught. So when it acts on ket 0 and 0, ket 0, 0, depending on the state of the first qubit, it will flip the second qubit. So I will get 0 for the first one, and the second qubit will remain as it is, right? Because the first qubit is 0. But when I act this CZ on 1, 0, then in this case, because the first qubit is in the state 1, then my second qubit will be flipped. It becomes 1. It becomes 1, 1. And if I, for the other cases, if it is 1, 1, then this will be, what will be this? It will be 1. First one will remain the same. The second will get flipped because the first one was 1. And the last will be, okay, I don't have time, space here, 0 and 1. Okay, so that will be same as 0 and 1. It will remain the same. So can I represent CZ in the form of matrix, just like I have represented the X gate, I have represented the Y gate, Z gate. Even the Hadamard gate is represented as 1, 1, 1, -1, right? And I told you to work this out. And one of you have pointed out that there is a 1/√2 factor, so that it will be a unitary matrix. So what is the form for CZ? Let's work this out. Okay, so all of them are 2x2 matrices. So CZ is no exception. It's a 2x2 matrix. And now what are the elements? So these are single qubit operations, right? So hence they are 2x2 matrices, but CZ is a 2-qubit operation. So it has to be double the dimension. It should be a 4x4 matrix here. And we can see clearly that for the state 0, 0 and 0, 1, it acts like an identity. And how do we represent 0, 0? From the last session, we know that we can represent 0, 0 as 1, 0, 0, and 0. Correct? And 0, 1. So 0, 1 can be represented as 0, 1, and 0, 0. Okay, so we see that first element and second element, that remains the same in the input and output. So it will be an identity at the first two indices over here. It will be an identity. And what about the other two cases? 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. So the second state is flipped. It's something like an X gate. X gate flips the qubit, right? So we get an X gate kind of structure over here, 0, 1, 1, 0. And this is a unitary matrix, so other entries are 0. Other entries are all 0. So we have successfully derived one matrix form for C naught, or the CZ gate, right? And is this the only way? Now suppose I consider my control qubit to be not as the first one, but as the second one. Second qubit as my control qubit. Then what happens to this C naught? Will it remain the same, or will it differ? Okay, so you can just check it out. You can calculate what happens if the target qubit and control qubit are interchanged. What happens to the CZ gate? Okay, so with that, we will come to today's session. And we also discussed a couple of other things like measurements in different bases, and then quantum teleportation protocol in the last session, which sets the stage for us to discuss further about quantum advantage. Yeah. But before again I step into quantum advantage, discussing various algorithms that prove advantage over that prove computational advantage over the classical systems, I would like to show you a software implementation of quantum computing through IBM's Qiskit software development kit, and in which an interesting document about on superposition is like mentioned. I'll just show you that now. Yes. Okay, so I hope it's visible. So what is superposition? We discussed about superposition in the first two sessions, and today I'm going to reinforce that understanding more. And with the help of an example, that is a coin which is spinning. So superposition is something which is very unique to the quantum physics or quantum science. It's not something which we can understand using the classical ideas, but rather we need to have a change in our complete mindset to understand what is superposition. And how do we utilize the superposition? We use something called interference, or rather quantum interference, to leverage the effectiveness of superposition and make applications out of it. So in our everyday objects that we see, they have various properties like size, shape, color, they are all determined. If I keep my pen on the table, I know its location. It's exactly in that location. It cannot be another location. But if my pen was a quantum object, then I cannot say for sure whether my pen is in this location. I'm not looking at it, and I cannot say for sure whether I have kept it in that particular location. It can be in any location. It can be spread out, and it could exist in multiple locations at the same time, and that is superposition. But when I look at my pen, the very act of looking, it collapses the state of my quantum object, of my quantum pen. So it will choose one particular position or location to be in when I look at it, or in a sense I'm measuring it. So that is called superposition, and we can find an analogy. Even I mentioned it in the first session, like flipping a coin can be analogous to a superposition state. How is that? If I flip a coin, and if it is in the midair, I do not know whether it's going to fall heads up or heads down, right? I cannot know that for sure. So it is not exactly the same. Although it's a crude analogy, there are certain cases where this analogy fails. And now, with the help of this document, I'll just explain to you how it is failing, where it is failing. So this is publicly available document from IBM, and it's very interestingly, they have pointed out with the help of the coding platform Qiskit. So when in the classical case, if we observe, when a coin is tossed, it can fall in with its heads up or heads down, and I can assign a probability of half. If it's an unbiased coin, there is a 50% chance for the coin to fall down with heads up, and 50% chance for the coin to fall with tails up or heads down. Okay, so I can write the probability as 1 by 2 times heads up plus 1 by 2 times heads down. Right, where 1 by 2 is the probability. Now, note that this is in contrast with how we write the superposition state, because in the superposition state, although we use the get sign as it is shown here, we take the square of the coefficients as the probability and not the coefficient as such. Now, I have a code routine here. So this is common in the Qiskit software SDK. So what we do is load certain libraries such as a NumPy, matplotlib for plotting, and a random for generating random numbers. Okay, and I perform the coin flipping or the coin tossing 1,000 times, and that's represented by n flips. And I plot a histogram of how many times I got the heads up and heads down. Okay, so it's a completely random process here, 50% chance for both heads up and heads down. So I get a histogram such as this, where there's an equal chance for both heads up and heads down. All right. Okay. Now, in contrast, if we have a quantum situation here, I cannot write it as 1 by 2 times get 0 plus 1 by 2 times get 1. It's wrong when it comes to the superposition, quantum superposition. I have to write it as 1 by root 2 times get 0 plus 1 by root 2 times get 1. And the probability of getting 0 is the square of 1 by root 2, 1 by 2. And probability of getting get 1 or Okay, I'll share again. There's some internet interruption. Okay. Sure. Okay. Okay. So what I do, I define a variable uh, for writing my quantum circuit, and that is Qcoin. And the argument of quantum circuit of is 1. 1 represents, I'm only passing one single qubit here. There is only one single qubit. So I'm defining a quantum circuit with a single qubit. And next, I perform operations on this qubit. So first operation is qcoin dot h of 0. H represents the Hadamard gate. Yeah, remember we learned about Hadamard gate, and it acts on 0. 0 is the 0th qubit. It stands for 0th qubit. That is the only qubit which we have in the circuit. And finally, I do a measurement of that particular state. So in Qiskit, by default, all the qubits are initialized to get 0. So the Q coin the 0 of 0 is get 0 quantum state, and then I apply a Hadamard on that particular qubit. So what happens? And then I measure it, and what happens? So I get this is a quantum circuit of what I defined right now. This is the qubit, and it is applied by the Hadamard, and then this is the measurement gate, and the measurement results in a classical state, just like I measured my pen's location, and it location, and that location is a classical value, right? And that is no more superposition is there. So it's a classical value. I store it in a classical way, represented by a line. Okay. So now what I do is I sample this system, which means I perform 1,000 times experiments, 1,000 times coin flipping we did before, right? So similarly, I do this 1,000 times, and the resultant values which I get, I bucket it in a histogram. And for that, I do something like I define a state vector sampler class, and I define an instance of that class sampler, and then I do something called that Qiskit pattern. I Qiskit. All right, I'm not sure why there's interruption again with okay. So now when I measure the qubit, I get two states. I get a 0 and I get a 1 with almost equal probability, 50-50, just like in the case of a classical coin flip. I again repeated this and I got an even better ratio of 0 and 1 outcomes, closer to 50-50. And next, what I do is I measure the expectation value of the states which I get, right? So I'll just use So I have, when I do a measurement on a system, it's normally done by default using a Z basis. And Z basis is a 1, 0, 0, -1 matrix. And when I measure the get 0 and get 1, it basically applies this matrix upon these two vectors represented by 1, 0 and 0, 1. And what I get is when Z acts on get 0, I get back the same uh, state vector, and when Z acts on get 1, I get a negative of the vector, negative of get 1. So here it is supposed to be a 1 plus 1, and here it is a -1. So these are the eigenvalues of Z operator. And when I measure the state with a Z or a Z basis or Z operator, the value which I get is this value +1 and -1. And if both of the states are occurring in the same proportion, like 50-50, then I would be getting 1 and -1 in the same proportion, and it will cancel out. Both of them will cancel out. So that's the idea. So now I move to, yeah. Okay, so here what I'm doing, I'm loading some additional modules and classes from the library, such as state vector estimator. This will help us in calculating the expectation value, and I'm also loading poly, sparse poly, op. These will help us to define the Z basis, and then the quantum circuit. So as before, I define the quantum circuit and I apply the Hadamard gate, and then I start using the estimator for calculating the expectation value. And then I define the Qiskit pattern. Now I have an additional argument called observables, which is defining the observable or the operator, or the operator whose outcome we are interested in, and that is a Pauli Z operator. And we write the job, and we pass the Qiskit pattern to the job and print the result. The result is obviously 0. Why? Because we already saw that if we have an equal proportion of both get 0 and get 1 in the measurement outcome, and the eigenvalues or the measurement values of these two states are 1 and -1 respectively. So they cancel out each other to give 0. Okay, so I get 0 there. So this is the same situation as in case of classical coin tossing. So are they both same? Because when in the classical situation also, I toss the coin, I get 50% heads up and 50% heads down. And in the quantum case, I applied a Hadamard, which can be called equivalent to the tossing of the coin. I get an equal percentage of getting 0 and equal percentage of getting 1. However, there is a tricky difference between both, and we will understand that through a thought experiment like this. Suppose the coin is flipped in the air, and I catch the coin using my hand, sandwich it between my hands, and then I check the side of the coin. It would be either heads or either tails, right? I cannot now use the word heads up, heads down, because it is not up, because I caught it in the x direction, along the x direction or horizontal direction. So it's either heads right or heads left, right? So in the case of a classical system where I am tossing a real coin and catching it in the midair, so I always get a 50% chance of heads left and heads right when I sandwich my hands and catch hold of the coin. But let's see what happens when you apply when we do that in the quantum case. And first of all, is it possible to get such a situation in quantum? Can we measure the state in the along the x direction? Yes, indeed we can do, and that is the function of x gate, right? So the x gate measures along the x direction. Similarly, z gate measures along the 0 1 axis. X gate measures along the plus and minus axis. Remember the block sphere which we discussed? So so instead of passing Pauli z, now we pass Pauli x to the observable, and then we run the system, and what we get is an answer of 1. That is the expectation value. So what does it mean, getting a value of 1? So again, if I go back to yes, here I write x, which is represented as 0 1 1 0, and now if I act x on the plus get state, I should get plus get. So why is that? Because plus get is 1 1, right, divided by 1 by root 2. So if I act on this, I'll get the same state, 0 1 1 1 equal to 1, and 1 1, and plus 0 1 equal to 1. Again, I'll get the same state with positive sign. And now what about get negative? So this is 1 and minus 1. So I get minus sign and get minus. So if I have a state, quantum state in get minus, and I measure the state along the x, or in other words, I use x operator to measure it, then I will get a minus 1. This is minus 1 and this is plus 1. Equivalent to the cases where I use a z-basis measurement and get 1 and minus 1 for get 0 and get 1. Okay, so yeah. And so if I, in that case, I will be getting a 0 value if if both of the situations get plus and get minus are occurring in the same proportion, then I would get a 0. But interestingly, it is 1. It's not 0, which means that the get plus state is predominant because the value of get plus is 1. Measuring get plus is 1. So we can understand this by noting that there is a difference between the quantum state and the classical state. Yeah, it's not. So in the classical state, if I catch the coin in the midair, there is an equal chance of heads being head, that coin showing head right and head left. But in the quantum case, if I measure the state of the quantum state being in the get 0 applied by Hadamard, so which is equivalent to the coin flipping in the air, and I measure along the x direction, I get plus as the only state. I'm not getting the get minus also in my measurement. So it's a single state is not a superposition at all in the X basis. Right. So it is different from classical situation in that way. And so the difference, what is this difference really coming? Where is this difference really coming from? And there's a crucial concept called quantum phase. So we know that every complex number can be written in terms of its magnitude and angle, such as Ci is a complex number. I can write it as mod Ci times e to the power I phi I, where mod Ci is the magnitude and phi I is the phase. And just like waves interfere, which I told you, the crests and troughs of the wave, and they match and unmatch to form constructive interference and destructive interference that results in enhancing their intensity and completely cancelling out their intensity respectively. We can make this analogy to a quantum state as well, because quantum states can also interfere constructively and destructively with respect to the phase between its basis states. That is called the relative phase. So when I apply a Hadamard, so the state becomes in superposition, ket 0 plus ket 1. And the relative phase between them is is 0. There is no difference in phase. But when I apply a second Hadamard, what happens to it? That's an interesting experiment that is carried out here. So we are applying 2 Hadamards, okay, like this. And this is equivalent to I am flipping a coin, and as the coin is flipping, I'm again flipping it, which does not make sense in the classical scenario. But for the sake of this experiment, we are trying to do this thought experiment to understand the effects of phase and interference on the quantum systems. So when the Hadamard is performed again on the state, which has already been in a superposition, so each of the ket 0 and ket 1 again undergoes a superposition individually. Ket 0 will turns out to be ket 0 plus ket 1, while ket 1 will be ket 0 minus ket 1. And note this minus here. So what it does is you have 2 waves now. One is that of ket 0 and one is that of ket 1. And ket 0 and ket 0 of yeah are in the same phase, so they enhance the ket 0, whereas ket 1 and ket 1 of these two are opposite. They are in the opposite phase. So when you apply the Hadamard on this again, so ket 1 will destructively interfere and it cancels out. And what we get is ket 0 as the answer. We get the ket 0 back. So we perform this experiment, sample this experiment by performing it 1,000 times, and the histogram shows that after applying 2 Hadamards, I get the 0 state back. There is no sign of 1. So this is quite interesting. So it shows how the interference work, and this is how we amplify the intended result in a quantum calculation and come to the solution of a problem. Okay, so in another situation here is another quantum circuit. I apply something, and it injects a phase difference into the quantum state which we are working with. So the qubit is first applied with a Hadamard and then a phase gate, which applies a pi phase difference and to the qubit, and then it's followed by another Hadamard and then a measure. So in this case, what happens here? Let's see what happens here. So this is to illustrate the significance of phase in quantum states. So when you apply a Hadamard, the ket 0, it becomes, I think I can write here. Yeah, so ket 0 is the initial state of ket q, and after the Hadamard, it becomes ket 0 plus ket 1. Okay, and after it passes through the phase gate p pi, what happens to it is uh, right, so it induces a negative sign here, that is a relative phase. I can also write this as minus ket 0 plus ket 1, because the point is there is always a relative phase between these two is formed, right? So minus is minus 1 is equal to e to the power exponential of I pi, right? So that is why applying a phase gate of pi results in a negative minus 1 phase difference between the two components. And then I apply a Hadamard on the state. So what happens? Now 0 becomes 0 plus 1, and 1 becomes 0 minus 1. So 0 becomes 0 plus 1, and ket 1 is yeah, so it's a bracket ket 0 minus ket 1. Okay, so now if I open this bracket, then we see that ket 0 cancels ket 0. So a simple act of introducing a phase difference, it cancels out the ket zeros instead of ket 1 in the earlier case. And the ket 1 gets enhanced. Ket 1 gets enhanced. And so when we measure this circuit, we will get a value of for 1 as opposed to 0. That's what we get. So let's see what happens when you sample. So yeah, so I sampled this particular circuit and then drew the histogram. And interestingly, I got for 1, I got full 1,000 values are giving me 1 as a measurement outcome. Yeah, so we can manipulate how much percentages of 0 and 1 should exist in our final result by adjusting the value of the pi, adjusting the value of the phase gate. So in this circuit here, I wanted, the problem is I want to find a 25% and 75% of 0 and 1. So what should be the value of pi? I'm sorry, what should be the value of phase I should use so that I get such a 25 to 75% result, right? So what should be the value of phase? It should be around pi by 3. If you can check it out. If you use e to the power this pi by 3, uh, and then if you apply the sandwich Hadamards on both sides, then the resultant state will have a 25% of ket 1 and 75% of ket 0 as shown in here in this histogram. Yeah, so 0 here and 1 here. So that way we will be able to design the quantum circuits by adjusting the parameters of our operators, right? So I introduced a new quantum operator here, or quantum gate operator here. It is called phase gate. And it does nothing much. It only introduces a phase difference between the phase states. Okay, so now let's come to today's main agenda. Okay. So we are here to discuss about the advantages quantum computers have over classical computation. To understand that, the very key idea is computational cost, and because a cost is very important to analyze whether a circuit is efficiently giving us a solution. It's not enough that our uh, solution circuit gives us the answer. It's not just an answer, but it should also be able to give it efficiently. And for that, we need to calculate the computational cost. This is calculated using using mainly by analyzing how many operations we are performing in a circuit. For example, I have an XOR operation here. So I use various gates to perform the XOR operation. And what does an XOR operation do? So it takes two inputs, two inputs, and it gives a single output, right? And it's basically a parity checker, which means if I give 0 and 0 as the input, the output would be also 0, right? And if I give a 0 and 1, then the output would be 1, because the 0 and 1 are not equal to each other, so it gives it gives a 1 value here. And similar to that, 1 0 will also output 1, and 1 1 will be a 0. All right. I use I think this is a very familiar circuit, so I'm not going into depth of this. So if I apply a NOT gate whose output is supplied to an AND gate for both the inputs, and then finally they are joined by an OR gate, and the output would be the XOR. So how many operations I am performing here? So there's an OR gate, and I assume that each of the operators have a computational cost of unity. So here I have one cost, and here another cost here. Yeah, this represents 1, and here another cost and another cost. So total 1, 2, 3, 4, 5. And now I also have additional costs due to the fan out gates here. So these are not really gates, but the act of going through these sections will take some time. So hence we associate a unit cost to these also. So in total, I have a cost of 7 for this particular circuit. Yeah, so basically, what is the 7? In fact, these gates, when the signals go through these gates, it takes some time to process the information within these gates. And so it is basically the measurement of time for the signal to pass through each of the gates. And also, these are not really these are not really the ultimate analysis of computational cost, because is this since these input signals are provided parallelly, they will take the same amount of time to go through this gate and this gate. They go parallelly. So if I don't have to calculate the cost associated with this gate and this gate separately, they are to be considered as same. And hence the actual complex cost is the one associated with this fan out diagram, fan out gates, and for the NOT gate another one, for the AND gates another one, and for the OR gate finally. So it should be a 4. 4 should be the cost. But we are not worried about that right now. We are just focused on how many elementary operations are there, and hence we go with the value of 7. And I'll briefly mention about the 4. This has got a special name. It's called the depth of the circuit, and it's a very sophisticated, advanced topic, and it's also a field of active research. But we are more interested in understanding the computational advantage of quantum. So we are interested in the scaling properties of such circuits rather than the exact computational costs. So depth is defined as a maximum number of gates encountered on any path from input to output. Okay, on the sidelines, I have also listed the length of the binary encoding scheme. So we can express any number in terms of its binary equivalent, such as 2 can be represented as 1, 0, 3 can be represented as 1, 1, 4 can be represented as 1, 0, 0, and equivalent to that, the length of the amount of bits I need to allocate for measuring these values also gradually increases. For 0 and 1, it's only a single length, a single bit is enough. But for measuring 2 and 3, I need to use 2 bits, which is manifested here as 1, 0 and 1, 1. And then if I want to represent 4, 5, 6, 7, or I want to calculate these numbers, then I must use 3 bits of memory, right? So the computational cost increases in that way with the length of the bits. And there is a formula for calculating the length. It is simply written as 1 plus log base to n with a ceiling around it. No, it's a floor with a floor around it, and that helps us to get these values. Okay, so with that, we are interested in the scaling of this cost rather than the actual value of the cost. So we can find that with the input length, the circuit complexity scales. For that, I'll take an example of bitwise addition, which all of us are familiar from our electronics classes, digital electronics classes. If we have 2 bits, let's say A and B, and we wanted to find the sum of these 2 bits, and we use a circuit called half adder to calculate the sum. And so the half adder outputs 2 bits. One is a sum and another one is a carry bit, right? So if I input 0 and 0, so these are A and B inputs, and these are the outputs S and C. So if I do that, I'll get 0 as the output of S sum, and carry will also be 0. But if I have 1 and 1, then here again the sum will be 0. So you can see that 1 goes here to XOR, and here 1 goes, and XOR 1, 1 is 1, and the negative of that will be 0. So S will be 0, and 1 goes here, 1 goes here, carry will be 1. Carry will be 1. And what about 0 and 1? If A equal to 0 and B equal to 1, then what will be the value of S? 0 plus 1 is 1, right? You get 1. And what about C? C would be 0. There will be no carry. C will be 0. And for 1, 0, we get the same results by symmetry. So in the case of 2 bits or single bits, addition single bits, we can use a half adder. When I use when I want to calculate the sum of more than 2 bits, let's say 3 bits. For 3 bits, I use a full adder, and the architecture of a full adder is as follows. It uses this half adder represented as HA, half adders, 2 half adders, and finally an OR. And if I want to measure for a 4-bit, if I want to add 2 4 bits, then I use such a scheme where I have one half adder for the least significant digit or bit, and then I use 3 full adders to get other binary digits and the carry bit. So if the complexity is calculated XOR from the last slide, we know it has a 7 cost, and for the AND has a 1 cost. And there are 2 fan out gates having each 1 1 each. So the total cost of the half adder is 10. And now I'm using the same half adders in full adder, inside the full adder. So there is a cost of 10 here, 10 here, and OR has a single cost. So total cost is 21 for a single full adder. Now if I try to add two sets of 4 bits, then I'm using one half adder, which has a 10 cost, plus 3 full adders. Each of them has 21. So 10 plus 3 into 21. Okay, now this can be generalized to an n-bit adder. For an n-bit adder, my cost of computation would be uh, okay, so it will be 10 plus n minus 1 into 21, right? 10 plus n minus 1 into 21. Okay, so the same thing I can rewrite as, so the cost is equal to 21n and minus 10 minus 21 minus 11. So I find that this is a function of n. So it scales with n. It has a linear relationship with n. Another way of writing this dependence of cost on n is order of n. I simply write it as order of n. Order of n. So for a adder circuit, I have an order of n. Now, what about other circuits like a multiplication circuit? So I'm not going into depth of that, but it is shown that it is having an order of n into m, where n represents the number of bits in the first number, and the m is the number of bits in the second number. And for the division also has the same order of nm. If both of the bits are having the same number of bits, it's equal to order of n square. Now there's another operation called integer modulo exponentiation, which is nothing but you take a power of a number n, and the power is k, which is a value, it's a number greater than 0. And the result you divide by m and take the remainder, which is also called as modulus of m. And such a operation has an order of complexity, order of n cube. Order of n cube is the cost scaling. And order all of these simple operations like addition, multiplication, division, and exponentiation, they have a polynomial cost associated with it. You can see order of n square, order of n cube. Now, there is another class of problem called integer factorization. What is integer factorization? Let's say I have a number 15. Can you find the factorize this number, factors of this number? So immediately we will tell, yeah, it is 5 into 3, right? So 5 and 3 are the factors of 15. So now I give a number such as this. It has got a name, RSA 2024. It's called RSA 2024. It's a very significant number in our life, for every one of us life, because it helps us store our bank details very securely. So this huge number is very difficult to find a factor for this huge number. And in fact, people have tried to find factors for huge numbers, not as huge as this, but a little less than this. And they were able to uh, find solutions using circuits which have complexities such as this and this. So they use trial division algorithm, which has an order of n square into 2 to the power n by 2, which is a humongous cost upon scaling. And a number field sieve, which is 2 to the power of order of n raised to 1 by 3, like that. So number field sieve has advantage over the trial division. because it is n raised to 1 by 3, and hence it is better than trial division algorithm. But however, both of these are having exponential cost. And now the solution to this is active research is going on in the classical field to find out algorithm which has only a polynomial cost and not exponential cost. Meanwhile, in the quantum algorithms, when in 1994, Peter Shor was able to show that this problem of integer factorization can be solved using quantum algorithms with a much better um, cost, which lower cost, and that cost is in polynomial. It is a polynomial cost. It is actually order of n cube. It's order of n cube. In order of n cube, Peter Shor was able to factorize large integers, and hence it's a threat. It's a threat to our current security protocol, which uses a large number like RSA 1024 to secure our privacy details like the bank account details. So people are actively trying to find out post quantum secure measures, such as a quantum resistant security, which means it will not be broken by any quantum. Okay, I'm back again. Okay. So in normal classical computation sphere, we know what in our schools and colleges, we have learned something called a von Neumann architecture, right? And that defines the computation such as this, where there is an input which is provided to a processor, which does a computation and it gives out an output. And the computation is the heart of it, and where it does all the calculations and calculations and analysis. However, there is another model of computation we call as a query model, or it also called as an oracle model. Why it's called an oracle model? So the function of the way it works is it has a computation unit, and it does not have the computation unit is not presented with the complete input. It's only presented with a part of the input, and the computation unit, it queries the input unit to get more information out of the input unit. So it's like an oracle. The input acts like an oracle, where the oracle is like an astrologer in our country, where he does not reveals everything about our future, but depending on the particular question which we ask, only to that extent the input reveals to the computation, and the computation calculates the output based on that. Okay, so there are some examples in the classical systems, like an OR problem. which is a function from an n bit to a single bit. So I have an input of n bits, like x equal to, let's say, get 0, 0, 0, n 0, 1, 0, 0, 0, and and my f of x will be a single bit. It would be either 0 or it would be either 1. Okay. So in our problem, what it does is it outputs 1 for the string x if the f of x is equal to 1. Otherwise, it will output as 0. So if we give a particular x value, and then we query the query, and we get the f of x of equal to 1, then it outputs 1. Then the computation or problem outputs 1, or else it will output 0. Now there's a parity problem where it also inputs the same. It also has the same structure for the function, and here it outputs 1 if the number of strings having f of x equal to 1 is odd. Otherwise, it will be 0 if the number of strings is even, which satisfies f of x equal to 1. So these are two classical problems of query models. There's a special class of problem called promise problem, in which a special guarantee is placed uh, upon the kind of function values. So if I have a function which takes n input n cube bits, puts a single, and I am guaranteed, or I am promised, that only one string in this n vector space, only one string of x has f of x equal to 1. Well, not a vector space. In this n space, I have only one string which has f of x equal to 1. So that is kind of a promise. There cannot be two strings for which f of x equal to 1. And what does this promise do? It helps us to simplify the computation. So I can do a randomized approach where I randomly choose an x and check its f of x value. And if it comes out to be 1, then it is I will be saved from doing more searches. Right. So in such ways, there are significant advantages, significant conveniences brought about by promise problems. In fact, in some of the quantum algorithms, like the Deutsch-Jones algorithm and also Simon's algorithm, they have a promise associated with them, and that promise uh, helps us to solve those algorithm, or implement those algorithm more efficiently, and prove a quantum advantage. So in the case of quantum computing, if we have to apply the query models in quantum computations, then we use something called a query gate. So I already told you about gates yesterday, and then I kept on adding a new gate every single time. Today I added a phase gate. Now there is another gate called query gate. So query gate is defined as follows. So it's quite easy to understand. So I'll say we are providing a string of inputs x, and these x are passed on to the query gate UF. And this UF has a function f of x whose structure we do not know. It is hidden from us. It's like an oracle. Its function is hidden from us. But only if we ask a particular question in the form of is x, then it will reveal the answer corresponding to that question in the form of f of x outside. But it is not simply I have a UF gate here, and I ask a question x, and it gives me f of x. That's not how in a quantum computation works, because it has to be unitary. This whole thing should be unitary, which means if I reverse this, unitary means it's reversible. So if I ask f of x, because unitary, I have already told yesterday, u dagger equal to 1, right? So if I ask f of x, then I should get back x. But what if f of x has x1, x2, x3? There are so many other values. So it is confused which one to input, output, right? If you reverse it. So it will not be unitary operation. So to make this unitary, we need to XOR the f of x with y. And then the question is, what is y? Y is called an auxiliary qubits. Auxiliary qubits are simply a workspace qubit. It helps, it assists us in the computation. So in the quantum computer chips, we have a set of qubits, right? And an architecture of qubits inside a quantum chip, integrated chip. And now, if the for every calculations, we cannot use only the minimum number of qubits and calculate the output, but rather we need the assistance from additional qubits, such as these auxiliary qubits, which takes up more number of qubits. So to perform a particular problem solution, we need not only a specific set of qubits required for our problem, but also additional qubits. So we need a larger number of qubits in our quantum architecture for solving problems. So today we have circuit architectures having hundreds of qubits, but in reality, to solve problems like Shor's algorithm and Gross algorithm, we need a very high number of qubits, amounting to millions of qubits. And the reason is we need so many ancillary qubits. We also need qubits which for error corrections also. Okay, and as I told you, the u tag or equal to 1, it also implies that the u inverse is equal to u. So that you can find out, which means u inverse is also a unitary function like u. So this is a reversible thing. And for making reverse, we need to XOR y with f of x. And the x will be spitted out without any change here. So this is how we implement query gates in the quantum system, quantum computation rather. So which leads us to the first quantum algorithm discovered in 1985 by David Deutsch. And he's called as a father of quantum computing because of his contribution. So this is a very simple system here. We are considered the unitary function is a mapping from single qubit, a single bit state to a single bit state. So we are giving an input in the single bit state, 0 and 1, and we get an output in a single bit state, such as one example is 0, 0. Another case is 0, 1. Another case 1. So all the 4 cases are listed here. Since we don't know the structure of the function, so the function can be any one of this. And if you notice carefully, these 2 states, the first and the last one, they are having a constant value, a constant f. No matter what input I give, it gives a constant value. But the center two functions are giving 0 and 1, 1 and 0. It's giving a balanced value. That means 0, 50% 0 and 50% 1. So in the case of single bits, it's quite trivial. But if we extend it to multiple bits, then we will understand that the condition of balanced, it becomes non-trivial there in that case. So here, what we can do, I'll just show a small illustration of how we can implement this particular algorithm using quantum gates. But before that, in the classical calculation, if I need to know what is the structure of the function, or rather than structure of the function, I need to find this find whether the function is a constant function or a function is a balanced function. That is the main question here. Is it a constant function or is it a balanced function? At least that much I need to know about the function. And in the case of classical case, I need to ask two queries. So I first I input 0. I input 0, then if I get 0 as the function's output, then it could be either this or it could be either this. So these two are ruled out, right? But still I have two functions to deal with. I don't know whether it is f1 or f2. So I again have to ask a second query, this is the first query and the second query. And now I find that when I put 1, it is again showing 0. So that means f1 of a is my function. All other three are ruled out. So I need to make two queries in the classical case to find out whether the function is constant or balanced. But in the case of quantum algorithm, or which is the Deutsch algorithm, I need to make only one query to decide whether the function is constant or balanced. And that's the advantage we are talking about of quantum algorithm over the classical one. So this one query advantage is never possible in classical system. It's never possible. So that's what that's the second quantum revolution. So I will just illustrate a little bit how we okay. So the circuit for the Deutsch algorithm is as follows. So I pass my ket x is the input, okay, in ket x here, and then I have an auxiliary qubit. Normally it is a ket 1, and both of them undergoes a Hadamard, and then the unitary gate, the query gate, and then only our x, this particular one coming from the ket x, this qubit line here, this is a 0 qubit line and this is a 1 qubit line. So that undergoes an Hadamard, and finally it's measured. Okay, it's measured onto some classical classical bit line. So if I do the calculation here, suppose my ket x is a ket 0, okay, which I will take into account in the later stage. So I apply a Hadamard. So first of all, using the Qiskit convention ordering, so I represent the bottom qubit in the left side. So I write this as 1 and x. Okay, so I consider them to be a 2 qubit system. Okay, and I represent it as 1x. And now I apply Hadamard. So what happens when I apply a Hadamard? So the 1 becomes minus, and this remains x, right? Okay, and then I apply a UF. So UF will take this y and XOR it with f of x. Right. So so after UF, so minus can be written as 0 minus 1, right? So after UF, I will get something like the 0 XOR with f of x minus 1 XOR with f of x. Okay, so this can be written in the form of when you have an equation like this, a formula like this, then you can write this in the form of minus 1 raised to f of x get 0 minus get 1. Let me just check 1 second. Yes, correct. So this is not tensor product. Okay, so this is XOR. Okay, so I have this now, and then I apply a Hadamard here on the first qubit. So yeah, so here there is also our x is also there. It will be here. Get x will be here, right? So get x here. Okay, so now I apply Hadamard. Now I make the assignation that x is equal to 0. And when I apply Hadamard, it becomes get 0, get plus, right? So it becomes minus 1 raised to f of x, or rather f of 0. And this will be get 0 minus get 1. And this will be get plus, which is get 0 plus get 1. Okay. Okay, so what did I miss? This thing. Okay, so you can check this, and what we get finally is something like so minus 1 raised to f of 0 plus minus 1 raised to f of 1. So somewhere f of 1 also is generated on the way, and this times gets 0. Plus minus 1 raised to f of 0 minus 1 raised to f of 1 get 1. And then I measure the qubit, the x qubit. So I get either 0 or 1. And now if I get 0, it means that this function here, this is non-zero, right? So this is non-zero means that so this function is kind of is balanced. Okay, so I get something like if I take minus 1 f of 0 outside this bracket, then I'll get minus 1 raised to f of 1 XOR f of 0. And if it is non-zero, then f of 1 XOR f of 0 will be even. It will be even, because odd, if it's odd, means this will be minus 1 and it will cancel out. So it is even. And if f of 1 XOR f of 0 is even, then that means f is constant, right? And if it is odd, that is what happens in the case of if I get 1 as the outcome, then f of 0 XOR f of 1 will be odd, and that means f of 0 and f of 1 are not constant, they are not equal, they are different, they are balanced. So with just one single query, which is x equal to 0, I was able to determine that f of 0, f of x is a constant function or a balanced function. Okay, so there are two key things coming into picture here, such as the phase kickback phenomenon, and quantum interference is very clearly observed in the calculations. So how different states are getting constructively enhanced or cancelling out because of our gates, different gates being used, including the UF gate. That is vividly observed here, and also something called phase kickback phenomenon, which is a little tricky. The reason is I initially here, when I wrote this system as this, I got a phase 1 minus 1 raised to f of x into ket x. So basically, I'm measuring only this particular qubit, right? But still, I'm getting the effect of minus 1 raised to f of x in my measurement, which means there is a phase kickback. I'm not measuring this ket one, this particular qubit line. I'm just measuring this one, but I'm getting a phase included in this x due to the effect of using a ket 1 here. If instead of ket 1, if I used ket 0, then I'll not be getting this minus 1 here. So that is the idea. So this is how quantum advantage was established by David Deutsch, in 1985, and following which various other implementations, such as Deutsch-Joes algorithm, which is an extension of Deutsch algorithm for n bits. So here I used only one single bit, get x. So Deutsch-Joes algorithm used n bits instead of single bit. And then there are other algorithms like Simon's algorithm, Bernstein-Bazirani algorithm, all of which have shown advantage over classical algorithms for certain problems. And then later on, the Simon's algorithm especially has a significant advantage, and it also inspired Peter Shor, to come up with an algorithm that can factorize large integers, prime numbers, which is a significant milestone. And after that, in 1996, Grover, who is actually an Indian, he also came up with an algorithm, Grover's algorithm, for searching an unsorted list, searching for a single key in an unsorted list. And he was able to increase the speed of that search. And that particular advantage is termed as a quadratic advantage. In a classical system, such a searching will take order of n complexity to perform, whereas Grover was able to perform the computation with an order of square root of n, having a marked quadratic advantage over the classical computation. And very recently, someone has also improved upon Shor's algorithm and was able to come up with a better algorithm to find out the integer factorization. So the field is still open, and active researches are going on with this. So this is a brief introduction to this quantum advantage which I wanted to talk today. And so I think we can take up questions now, as the time is almost up. Do we have any questions? If there are any questions, you can raise your hand.
Hello, sir.
Hello.
Sir, am I audible to you?
Yes, Amraj.
Okay, sir. Actually, you given a very wonderful presentation about the quantum technology, and also you have demonstrated about how it can be taken into Python programming. So, but I want to know one thing, sir. Like with respect to the time complexity of the algorithms or code, how we can prove our quantum cryptography can take less time in the code level, I'm asking. How we can integrate that? Because I'm running with a laptop only. Okay. The same infrastructure only we are using that. Then we have our traditional programming. And when I go with what the Python for this quantum programming, then how I can able to differentiate them with respect to the time.
So are you using a quantum algorithm to perform the...
Sir, actually, I just seen your flow. Actually, I gone through that. Okay. Actually, I'm looking for some materials also, but in the portal, I couldn't get it. Okay. But when I seen your Python-based demonstration, okay, it is what actually, when we have some advanced infrastructure like quantum computers or servers, we can able to find. But actually, we are using our own laptops only. Then how we can able to demonstrate that? Because suppose if I'm going to do a research on this, how I can able to prove my results?
Okay, so
research perspective, I'm asking, sir.
Okay. So I think as I already mentioned, the quantum cases are very different, right? So as we are not given these ideas about how to how to deal with the query models and query models computation. So these are quite new to us. Right. So I think before getting into the coding, if we have a basic understanding about these new models, it will help us to structure the coding accordingly. And also, it's not possible to straight away write the code unless we get some exposure to some standard codes. So as I shown in the coding session, some of the codes are shown to you, right? So from like that, there are codes for, let's say, Deutsch algorithm. So if we go through that, it's available in the internet, so you can go through that, try to code yourself. That will be a learning curve, and it will help you in the research of some other algorithms and things like that.
Okay, sir. Thank you, sir.
Yeah, sure. Milan, you can. Okay. So I see there are two more people have raised their hands. 2 or 3 people.
Hello, sir.
Hello. Yes, please ask a question.
Sir, can we work on QCA? And what is the difference between QCA and these qubits?
QCA is something new for me. I don't know what is QCA.
Quantum data cellular QCA 2.0.3 software, sir.
Okay. Okay, I'm not aware of that actually. And something new for me. I'm not aware. I've not heard of that.
Sir, quantum.cellular.atoma. Okay, sir. Sir, in this quantum computing, there are many research areas, sir. So I belongs to electronics engineering. How can I search the research topics for electronics engineering?
You mean in alignment with quantum?
Yes, sir.
So I think you can you can sign into the IEEE, and they have a lot of updates regarding that. IEEE is basically an electronic society, but they have also forums for quantum related stuff.
Okay, sir.
You'll get information from them.
Sir, but when we are doing on this, we have to pay amount for IBM.
Yeah.
When we are working on qubits. Is there any free sites for working on this?
Not I know. I use IBM only.
Only IBM. Okay, sir. Thank you, sir.
Hello.
Hello.
Hello. I am Dr. B. Faisal from KMIT, Hyderabad. Am I audible?
You are audible, but it's a little slurred. It's not very clear.
Okay.
But I can hear you.
Okay. Okay. So I have a very fundamental doubt, sir. Actually, Y gate is 0 minus I 0, if I am not wrong. Did I mistakenly listen to your thing as 0, 1, minus 1, 0? You have written 0, 1, minus 1, 0. I was checking myself. Y poly Y gate, it is 0 minus I 0. Am I correct, sir?
Can you just repeat again? Is it
Y
available?
gate, Pauli Y gate matrix.
Okay, the Pauli Y and Z.
So we have discussed the Pauli X, Y, Z. So in Pauli Y, yesterday also I wanted to raise the hand, but it's not. And today also when you are giving recap, you have written the same thing. You have written 0, 1, minus 1, 0. But if I am not wrong, Y is 0 minus I 0.
Okay, so it doesn't matter because these are unitary operations, and we are concerned with the modulus square of the coefficients, right? So if I take the coefficient 0 square plus 1 square, that will give me 1.
But
And
if
if you get this
I
right,
operate this Y gate on ket 0, it gives me I ket 1, right? I ket 1. So if there is no I in the matrix here, how do I get I ket 1? The mapping is ket 0 maps to I ket 1. Ket 1 maps to minus I ket 0. As far as the Y
it is not ket
concerned.
1, it is ket I. Ket I and minus ket I. I mean, ket minus I.
Okay.
Yeah. These are the eigenstates.
Okay. So you are including in the states itself. Okay. So
Yeah,
I'm saying, I get 0, so you are writing it as basically cat I.
yeah, cat I.
Okay, sir. Thank you.
Because cat 0 and cat 1 are not eigenvectors of y. These are not
Yeah.
eigenvectors of y.
Okay. Another thing, anyways, the previous speaker had asked and you had answered. We use IBM only, but earlier it was giving us the option to run also, but right now simulators are not available. We can
What's
only
okay?
we can only build a circuit and do it, but running the implementation is not accessible as of now in Qiskit IBM.
Yeah, so for the learning purpose, we can use the simulator. It will help us to understand because it has the same, it has combined the
No,
same properties, including errors,
even
error
simulator
correction.
is not available now. Earlier, we used to work on QASM simulator. There
Okay.
were other simulators also, but right now simulator is also not available.
So IBM has changed some platforms. Yeah. So if you sign out from the older one and sign into the new platform, and then it would be coming available.
Pardon
But,
me? Can you repeat?
if you sign out from the earlier one and sign in, start a new account in the new platform, it will help you to start a new account.
Start a new account.
Yeah, new
Okay.
account. Yeah.
Okay.
Yeah, and the hardware is still limited, but I think the simulator should be available, definitely.
Okay. Thank you so much.
Thank you.
Hello, sir.
Hello.
Sir, in general, quantum computing executes faster than classical computing. But when I'm working on images in quantum domain, it is taking more time than classical methods. So what will be the reason, sir?
It's not a general rule that quantum computing works faster than classical computing. So that's why I'm showing specific algorithms, like Deutsch algorithm, Shor's algorithm, Gross algorithm. These specific problems have a quantum advantage.
Okay.
Yeah, not all the problems have a quantum advantage.
Oh, okay, okay, sir. Thank you, sir. Thank you.
Thank you. So tomorrow we will discuss about the hardware part. As I said yesterday, that today will be software oriented session and tomorrow will be a hardware oriented session. So we will discuss various platforms such as how to implement the qubits in a physical hardware chip, like semiconductor qubits and so on. So if anyone of you are interested, you can work out this implementation. I was not able to show this completely. So you can try this out for yourself. This is Deutsch algorithm implementation. Okay, so I think this is how we have to solve this. So minus 1 raised to f of 0 plus minus 1 raised to f of 1 into times get minus and into okay, sorry. So into get 0 plus there will be minus 1 raised to f of 0 xr f of 1 here. Times get 1. Okay, so so you can solve it like this. I think I have missed one term here. So if you include that, then it will be able to. So this is the pathway. You follow this, should be able to find the answer. Okay, so that's it from my side today. We will continue tomorrow with the hardware implementation side. Thank you.
Yeah, thank you, sir. So we'll wind up for the day. We'll meet again by tomorrow at 3 p.m. Thank you so much for your informative session. So yes, dear faculty members, as the same, I'm just repeating. Please mark your attendance without any fail, as 60% of attendance is mandatory to get a certificate. And some are asking for yesterday's and day before yesterday's attendance link, which can't be shared. As already informed, the attendance link will be active only till 5:30. Yeah, the attendance link I have shared once again on the chat. If you have missed out to mark, kindly mark your attendance without any fail. And please use the same mail ID to mark the attendance. Every day you have to mark your attendance with the same mail ID. Okay, then fine. We'll wind up for the day. We'll meet again by tomorrow at 3 p.m. Thank you all. Thank you for joining. Thank you.